Hello and welcome to another video from Professor Watts. We are going to be doing an overview of Module 9 in the Differential Equations course where we look at Laplace transforms. Let's first look at the notation for Laplace transforms. We'll start with a function y as a function of t, and then when we take the Laplace transform, we denote that with a capital L, L for Laplace. And then use function notation. The transform operates on an input function. So y is the input for the transform. And then the output is a different function, which we denote with capital or big Y. And the independent variable changes from t to s. And in general, we use a lowercase letter for the initial function. The Laplace transform will use the same letter, but the capital version of that letter. Laplace transform has an inverse, and so you would start with a function of s, and then when you take the inverse transform, you denote that with a capital L exponent -1, similar to the inverse function notation. And of course, that's operating on big Y, and the result is little y. And so the independent variable does change as we go from t, which is often denoting time, to this independent variable s. So how do we actually transform a function with the Laplace transform? The Laplace transform could be defined with this integral formula. The Laplace transform of y is the integral from 0 to infinity of the base e exponential with exponent -st, where t is your function, the independent variable of the function you're transforming, and s is the independent variable of the result. And then you multiply that exponential with the function itself, and you integrate with respect to t, or whatever the independent variable is for that function. All right, let's try that out with an example. What if I have the identity function y of t equals t? Well, then I would replace y of t with the integral with t. And in order to calculate this, we would need to use integration by parts. If you're familiar with integration by parts. With integration by parts, we are integrating two functions multiplied, two factors, and one of them you will take the derivative of, and one of them you will integrate. And the result, you get the one you're taking the derivative of times the integral of the one you're integrating minus the integral of the derivative of the one you're differentiating. And again, the integral of the one you're integrating. So you want to identify which factor will be differentiated and which will be integrated. And of course, if there are limits of integration, then those same limits appear on the second integral and evaluated on the part outside the integral using the fundamental theorem of calculus. So for us, we want to take the derivative of the t part, and we want to integrate the exponential. Right? So when we start, we just have the regular t, the part we're differentiating doesn't change, and then we go ahead and take that integral, which would be the exponential divided by the chain rule part. So we get t is your variable here, and so you get over a -s, and that gets evaluated from t equals 0 to infinity. And then we take the derivative of t, which gives us a 1, and again, use that integral. Negatives cancel. Let's put the 1 over s there. And that integral is pretty easy to do. Integral that you just get another -1 over s. So when you evaluate at the infinity, both of these are going to be 0 um, because t being replaced with infinity or t going to infinity gives you e to the negative infinity, which is 0. So with both parts here, you get 0 for the upper limit. Now for the lower limit, you get 0 in the first part because it's got a t, and we're evaluating at t equals 0. So that whole thing is 0. But you don't have that t in the second part. And so when t is 0, e to the 0 is 1, the exponential goes away. And we do have a 1 over s and a negative 1 over s, which is a negative 1 over s squared. And there's already a negative there from subtracting the lower limit. So you end up with a positive 1 over s squared. So the Laplace transform of t is 1 over s squared. All right, why don't you try using the formula? Go ahead and write that formula down. And pause it if you need more time. And try taking the Laplace transform of the constant function, y of t equals 1. All right, pause if you need more time. You should just get the exponential function there. And the integral of that exponential is just going to give you the 1 over s. So the transform of 1 is 1 over s. And that's covered in the book if you want to see that worked out. Section 8.1, example 8.1.1. So these integrals are tough even for basic functions. And so most of the time we'll actually be using a table. There's a table linked here and in the book, table 8.8.1 of some Laplace transforms. It is. And the source function as a function of t is in the left column. The Laplace transform as a function of s is in the middle column. And then there are restrictions on the sign of the independent variable in the right column. You can see in that first row, the Laplace transform of 1 is 1 over s, the previous example. And then the second row covers all monomials. And when n equals 1, that's the Laplace transform of t, gives you 1 factorial over s squared, which is 1 over s squared, our first example. Notice you can take Laplace transforms of polynomials, trig functions, well, sines and cosines, and then the hyperbolic sines and cosines, and the base exponentials. You also notice that the Laplace transforms are often rational functions. Now, there's a formula for taking the inverse transform of a function of s, but it is beyond the scope of this course. So we will exclusively be using technology or the table to take the inverse transform. That still doesn't make it trivial, as finding which row and then how to adjust the formula can be tricky. Consider this example. What's the inverse transform of big Y of s equals 9 over s squared plus 9? So we'd be looking for this type of function in the middle column of the table. Do you see where that might be? Pause if you need more time. You should have honed in on the sines and cosine rows. Now for cosine, you actually get the s variable in the numerator. We have a constant, so we'd want the sine row. And so the inverse transform of omega over s squared plus omega squared is sine of omega t. That would be the formula we would use. But even having that, we need a little bit of work to be done. So the Laplace inverse transform of omega over s squared plus omega squared is sine of omega t. Now, we kind of see that we'd want omega to be 3, since we've got a 9 there, and that's 3 squared. But we don't have a 3 up in the numerator. So we would need to think of writing that 9 as a 3 times 3. And so we can keep 1 factor of 3 there, and then have 1 factor of 3 just brought out front. So then when we take the Laplace transform, the inverse Laplace transform of 3 over s squared plus 3 squared, we do get sine of 3t. And then that extra 3 can be brought out to give us our final result. Answer choice C. Now, what we want to do is take the Laplace transform of a differential equation. And so we need to take advantage of that linearity that we just used with the inverse transform. So when we take the Laplace transform of this, we can essentially distribute the operator to each term. And this works for the transform and the inverse transform. So that's one of the properties of linearity. The other is that constants can be brought out front. And we've used both of these properties with derivatives and integrals. So it should feel natural. So bring that 5 out, bring that 6 out, and we can bring that 10 out. Let's practice using the table to find the Laplace transform of e to the t cosine t. So we're looking for e to the t cosine t in the left column of the table. And you see here, it's written where you can have coefficients lambda and omega. Those are both 1 for us. So we'd use this formula for the result where lambda and omega are both 1. So we can take the transform of the forcing function on the right side. And of course, we know the Laplace transform of y is big Y of s, but the Laplace transform of the derivatives are still unknown. So how do we take the Laplace transform of y prime? Well, we can use the definition, that formula, replacing the input function with y prime, we get this. And again, we'd want to take advantage of that integration by parts technique. However, here, we're going to want to integrate the y prime, since it's a derivative. And then we'll want to differentiate the exponential. So again, we don't actually take the derivative on that part the first time. And then the integral of y prime is just y. And then that's evaluated from 0 to infinity. And then when we do take the derivative of e to the negative st with respect to t, we get a negative s from the chain rule. And again, we use the integral version of that. And that's also going from 0 to infinity. And then you may recognize that this is the Laplace transform of y, right? With an s out front. So if you put that s there, that just the integral, that is the Laplace transform of y. And so it could also be written as like that. Now, what about this first part? Well, if we evaluate the upper limit when t goes to infinity, then for any value of y, the exponential will go to 0. So you get 0 minus, and then when we evaluate at t equals 0, the exponential goes to 1, and y is evaluated at 0. And we usually write that y of 0 over here. So the Laplace transform of y prime is s times the Laplace transform of y minus the initial condition y of 0. Now, we're not going to go through the process for the second derivative, but you can find that, and it just would repeat this process twice with the integration by parts. The result for the second derivative, you get an s squared times the Laplace transform of y. And then you get the other initial condition coming up. So again, these are initial value problems for second order ODEs. So we should be given y of 0 and y prime of 0. So these initial conditions get sort of baked into the formula. And so we actually go right to specific solutions when we solve this way. Also notice there is an s in front of the y of 0 here. So you typically just memorize these formulas, but you can derive them using that formula if you forget. All right, so that's enough to get through some basic differential equations, which is covered in the first methodology. But ultimately, we want to explore forcing functions that are novel and could be piecewise continuous or even discontinuous. And the key to doing that is to express piecewise functions in terms of unit step functions. So the unit step function is zero up to a certain point in which it jumps up to one or steps up to one. So here you see the unit step function that is zero until you get to the t value tau, and then it steps up to one. And there's two ways to write that. You can, they both use the lowercase letter u. You can do t minus tau in parentheses, or you can just use the tau as a subscript. The subscript one's nicer because it's less to write, but you want to know both for reading books and stuff. So, this would actually be some value. Maybe it's a 3. And if that's the case, we could write u of t minus 3 or just u sub 3. So that's the unit step function that steps up when t equals 3. So how are these used to help us with piecewise functions? And here's a piecewise function. You can actually write these in terms of unit step functions. Now, you don't really need a unit step function for less than 0 because these initial value problems start at 0 and then they just go to increasing values of t. So we're not really concerned when t is less than 0. You could put a u of t minus 0 or u of t there, but it shouldn't really change it. So usually that first unit step function at 0 is dropped, and you just write the first piece, which is 2t plus 1. Then when you get to the second piece, you want to put the value of the function there, but then you need to subtract the first piece so that when you're at values where t is greater than 2, the 2t plus 1 and the negative 2t plus 1 add to 0. And then you can see I'm using the subscript version of the unit step function that steps up at 2. So let's just quickly explore this and make sure it works. So if, say, t was equal to 1, and I'm evaluating at t equals 1, then I would get 2 times 1 plus 1. And then in here, I'd get 3 times 1 minus 2 times 1 plus 1. But the unit step function u2, it's 0 whenever t is less than 2. And so it's a 0, so this whole thing is gone. So then you would just go to that first row in the piecewise form, right? Which is what you want. When t is less than 2, you're just going to get 2t plus 1. All right, what if t is greater than 2? Let's try putting a 3 in there. So we get 2 times 3 plus 1, and then 3 times 3, 2 times 3 plus 1. And then the unit step function that steps up at 2, if t is 3, that's greater than 2, and so it becomes a 1. So then this stuff is here. So it's like a switch. It switches on at this number, 2. Goes from 0 to 1, and so it kind of turns this piece on. And then the 2 times 3 plus 1, which is 7, you subtract that negative 7, and then those parts go away. And so you just get 3 times 3, which is the bottom row. So these are equivalent representations of that function. And using the unit step function, we can write it all in one line instead of having this kind of branched separation that the normal, parentheses systems notation has. So if our forcing function is piecewise, we can rewrite it using unit step functions. And then when we go in and take the Laplace transform, all we need to do is, well, take the Laplace transform of a unit step function. So how does that work? So here's a formula for the Laplace transform of a unit step function that steps up at a times some function of t, which we're calling g. And what happens is the unit step function gets traded off for an exponential base e, with a negative s times that value of a, whatever that is. And then you'll still need to take the Laplace transform of g, but before you do that, you'll need to shift it by that same value a. Let's take an example. So Here we take the Laplace transform of 2t plus 5 times unit step function that steps up at 2. And we know that the value of a is this, right? So that tells me that a is 2. So when I go to the formula, I'll do e to the negative 2s because a is 2. Now, before I take the Laplace transform, I need to shift. I'm going to add a, which is 2, to all the t values. So it's 2t plus 5. You need to replace t with t plus 2, right? That's t plus a in parentheses. So that takes care of the shift. And then I still need to take the Laplace transform, but let's go ahead and simplify. First, distributing the 2, and then 4 plus 5 is 9. Now we learned a couple of Laplace transforms earlier. Laplace transform of 2t, well, we can bring the 2 out by linearity, and then the Laplace transform of t is 1 over s squared. And then the Laplace transform of 9, you can bring the 9 out, and the Laplace transform of 1 is t. So now we have the Laplace transform of that unit step function times that other function. Now, we're going to be doing some other stuff, but ultimately those exponentials will stick around, and we're going to want to take the inverse transform and have those exponentials give us back our unit step functions for the final result. So how does that work? Oh, well, I guess I have an example here for you real quick. Go ahead and pause it if you need a minute. All right. Oh. All right, so in this case, we have a equals negative 3, right? So the unit step function is t minus tau, so that's t minus negative 3. So we would get an exponential of 3s, because it's normally negative sa. And then we take the 1 minus t, and we replace t in parentheses with t plus a, which would be t minus 3. Then you can go ahead and distribute, and you again will get, well, we can do it. So 1 minus t minus 3, you get 4 minus t. And the Laplace transform of 4 is 4s, and then, sorry, 4 over s. I think I messed that up on the previous one. The Laplace transform of 1 is 1 over s, so this should be 4 over s. And that previous slide, it should have been 9 over s, sorry. And then t is the 1 over s squared. All right. So going with the inverse transform, we're going to have those exponentials, and we're going to have some function of s. And so, of course, the exponential, where a is identified from the exponent being negative sa, that a will define a unit step function that steps up at a. And then you'll need to take the inverse transform of g, using a table, to get little g of t. And then after you take the inverse transform, you shift. So on the way in, you shift and then transform. On the way out, you transform and then shift. And the shifts go in opposite directions. Do we have an example? Here we do. All right, so first identify your a value. In this case, a equals 1. And also identify your g function. In this case, g equals s. Well, negative s, right? There's a negative there. So then we can write a unit step function that steps up at 1. And then we can take the inverse transform of negative s and unless I just picked an example where it's not in here. Yeah, great. So just a regular s does not appear in this list. So that example, let's change it to something that we can do. We'll make that a 1 over s. So we can actually do this problem. There we go. So now g of s is 1 over s. And maybe we're getting more comfortable with Those the inverse transform of 1 over s is 1. So g of t is just 1 here. Well, negative 1, right? Because there's a negative there. Now, when you do the shift, you're only doing it to the independent variable. So if you have a constant, the shift actually doesn't affect it. So if g of t is negative 1, then g of t minus a is also negative 1. I mean, think about doing a horizontal shift on a constant function. It's a horizontal line. It doesn't affect it. So, oops, long story short, this goes up here, and you just get a negative 1. So negative u1, which again, you can write that as t minus 1 if you want. All right. And I think that's it. Ready to go into the methodologies and see how to work with these Laplace transforms. But of course, we should attribute William Trench, author of Elementary Differential Equations of Adiabatic Problems. That textbook we've been using was in this presentation and is CC by NCSA. Thank you so much. I'll see you in the next video.